are going to scale the current or the geometry of the device and want to have a rough indication what will be happening. So we are going to use the devices, the CS stage, mostly in the saturation region, because there it has the highest gain. It has the best amplifying capabilities. So all approximations are only valid for saturation region. And we will look at the elements of the small signal model. CGS, as you know probably from device physics, is about 2/3 of the oxide capacitance, which is the width times the length times the oxide capacitance per squared unit of length. The feedback capacitance, CGD, is mostly formed by in the saturation region by the overlap capacitance. And here you see the specific overlap capacitance per unit of length times the width. So that doesn't change with current or voltage as long as we are in the saturation region. And it is completely scaled with geometry factors. The other things are a little bit more complicated. So IDS, GM, and GO. And that's why we study two cases. One is maintain the inversion coefficient and then do something with the device scaling, with geometry scaling, and see what happens with the parameters. And the other one will be maintain the current. So let's first maintain the inversion coefficient, which basically means that if you scale a device, you want to you keep the VGS such that the IG, the inversion coefficient stays the same. Well, what happens then? If you, here, the first two, they don't depend at all of the inversion coefficients, just does this one. If we increase the width, then it increases, IGS increases, because it's like we are placing elements in parallel. But it decreases with the length, IDL. GM is the same as IDS. And GO, stronger dependence on the length, because there are two effects that count for GO. One is if the current drops, the output conductance drops. But second is that if the length increases, the relative contribution of the channel length modulation becomes less. So the output impedance decreases, the output conductance decreases, the output impedance increases more. If you maintain the drain current, you get a little bit different situation. Well, here, of course, it doesn't matter what you do. Here, you have the same current, but GM drops. If you maintain the current, but you increase the width, then the current drops because you go to a lower inversion level. And if you increase the length, then the current drops also. We have seen that before, of course. For GO, it's the same. If you maintain the drain current, but you increase the width, then the GO drops. And if you increase the length, the GO drops even faster because you have the two effects. So this is basically a nice list of actions that you can do to achieve a certain